assignments, doubts, exams. We have got you back. EduPlanner make every chapter easy to understand. Stay tuned, learn more, grow with us.
In this example, we want to determine what the magnetic flux is through this single circular loop of wire that I've labeled C here. Given that we know the magnetic flux through a similar square loop of wire, which I've labeled S over here, that has been deformed into the circular loop. So we know the square loop in this constant magnetic field that's pointing into the page has a magnetic flux of 7 times 10 to the minus 3 Webers. So let's start just by writing or just remembering what the expression is in general for the magnetic flux for a constant field. It's just going to be the magnetic field B times the area of our loop times the cosine of the angle between our loop normal and the magnetic field, which in this case is just going to be the cosine of 0, which is 1. Since the field since the field and the area normal are parallel to each other. So really we're just looking at B times A for the flux right now. So for the square, we know that the area of a square is just going to be 4 times the side length. So the flux should be B times something like, or sorry, not 4 times the side length, but L squared. I was thinking of circumference. So BL squared. And then similarly for our circle, we're going to have the magnitude of the field B times the area of a circle, which is pi r squared. So up in our drawing here, we'll call side length of our square L. We'll call the radius of our circle R. Okay. So can we say anything about the relationship between L and R here? Because we don't really know anything about them. So we have 2 equations with 3 unknowns, it looks like currently, because we don't know anything about L. We don't know anything about R. And we don't know what the flux through the circle is. So the key thing to realize here is that since we deform our loop from a square to a circle, the total length of wire that we're using is going to be the same throughout. So the area might change, but the length of the wire does not. So the length of the wire is just going to be equal to the circumference of each of our shapes. So the circumference for the square is going to be equal to the circumference for the circle. And the circumference for the square is just going to be 4 times the one side length. And the circumference of the circle is just going to be 2 pi r. So if we divide both sides of that equation by 2, we'll have 2L equals pi r. Or if we want to even go further and divide both sides by 4 initially, we'll have L equals pi r over 2. Okay, so we have a way to relate L and R here, which should be helpful. So what I'm going to do now is show 2 different ways about figuring out what the flux through the circle is. The first one is I'm going to substitute out R in our expression for the flux through the circular loop in terms of L. So if we were to have solved this for R in terms of L, we could have just divided this equation by pi on both sides and had R is equal to 2L over pi. So if I substituted that into the equation for the flux here, I would have B times pi times 2L over pi squared. Or if we simplify that, we'll have B times pi times 4L squared over pi squared. So we can cancel out a pi and we'll just have 4bl squared over pi. And now what we're going to do is just compare this new expression we've made to the one for the flux through the square, which is just 4b times l squared. Actually, just bl squared. bl squared. So if you notice, they're almost the same, right? They both have a bl squared. The only difference is 4 over pi right here. So we could relate these two fluxes by saying that the flux through the circular loop is equal to 4 over pi times the flux through the square loop. And once we know this, if we have the flux through the square loop, we can easily solve for the flux through the circular loop. Now, the other way we could have arrived at this exact same equation was just by initially starting off and saying, okay, we want to look at the ratio of the flux through the circular loop to the flux through the square loop. And if we did that, we would have seen this comes out to 4 over pi, and we'd have the exact same equation. So now that we have this, all we have to really do is just plug in our value for the flux through the square loop and multiply it times 4 over pi. And if we do that, we're going to get that the flux through the circular loop is equal to 8.9 times 10 to the minus 3 Webers. So there you go. We determined the flux through this circular loop, given that we knew the flux from the square loop that we deformed into the circular loop.